Hello everyone, welcome to Knowledge India once again. In this particular tutorial, we are going to discuss about Transit Gateway, and we will try to understand that how can you use Transit Gateway to implement some of the advanced architectures. Normally what happens is in an enterprise where you have got a lot of VPCs in place, as you grow, it becomes quite difficult to manage things. We have done a detailed video which talks about the setup of Transit Gateway and usage of Transit Gateway to overcome the overall VPC mesh. So if you haven't watched it, you can watch that. We'll assume that you have understanding of all the VPC concepts already. In this particular tutorial, we are trying to understand some of the new types of implementations which you can do with the help of Transit Gateway and few other things. Okay, so let's move ahead and try to understand that. So first, let's understand a quick overview of VPC peering. As you might already know that via VPC peering, two VPCs can talk to each other, right? So it's a bi-directional connectivity. You basically set up the peering and then add the necessary routes in the route table, and after that two VPCs are able to talk to each other using Amazon's own private network. Now there is a charge whenever traffic is flowing over that peering, though there is no hourly infrastructure fee, which means if there is no traffic flowing you will not get charged, but whenever traffic flow happens you get charged, right? But one of the problems with VPC peering is that it doesn't support transitive routing, which means if VPC A, VPC B and VPC C are there, A is peer to B, B is peer to C, A cannot talk to C, right? Now, because of that, it happens that in an enterprise when you have a lot of VPCs and all of them need to talk to each other, it leads to a mesh type of structure. We have discussed this in the Transit Gateway video as well. So because of that, there is a limit, there's an upper limit that how many VPC peering connections can be there per VPC. It's not unlimited. So in big organizations, you can hit that limit quite soon. So what are the possible ways to solve that? There are two ways to solve that, right? Earlier people used to do Transit VPC. So in case of Transit VPC, what we actually do is we try to implement a hub and spoke design where you have got all your different VPCs as spoke, and you will create a central or a hub VPC which will call as Transit VPC, and basically there will be VPN connection or set up between every VPC and this Transit VPC. So on the VPC side, right, for example, if you see on this particular on the screen here, in these VPCs you will have VPN gateway, right? We use this VPN gateway whenever you have to create a VPN connection even with the on-premises data center, right? So in the same way you will have VPN gateway, or it is actually virtual private gateway is the thing which you will actually create in every VPC, right? And that will get used to create this VPN connection with this central VPC, which will be called as Transit VPC. Now this Transit VPC will have EC2 instances, and on that Cisco software would be running, right? So in this case, maintaining these instances, installing that Cisco software, and then setting up this VPN connection, all of that is your responsibility as a customer. You will have to do it. So people were doing this model earlier, but with Transit Gateway coming into picture, people are moving towards Transit Gateway because Transit Gateway is a managed solution and you don't have to get into any third-party software installation, right? So, and of course there are other benefits as well. And so now let's look at the Transit Gateway setup. Transit Gateway solves this problem for you because you don't have to really maintain some infrastructure which is running behind Transit Gateway, right? So you don't have to really maintain that Transit VPC type of thing. Instead of that, you can just use Transit Gateway. It's a managed service and you can manage all the VPC peering connections at one place, and your network doesn't become a mesh. That's the thing which Transit Gateway gives you, right? Not only that, you can do additional things, like you can use Transit Gateway to do on-prem connectivity, right? So let's say in this particular diagram, if you see on the screen, we have, like, let's say 4 VPCs here on cloud, and what you could do is you can just do one connection to the on-prem, either via direct connect or VPN connection, and then basically from all the VPCs, traffic will come to this Transit Gateway, and it can go to on-prem via VPN connection or the direct connect. So basically, you don't have to do VPN connection to every VPC. You don't have to, right? You can just do the on-prem connectivity and let it reach the Transit Gateway, and then from Transit Gateway, traffic can go to all the VPCs. You can do that easily, and it becomes a lot more cleaner. Okay, now Transit Gateway, it's a regional resource, and when it was launched, at that time it did not support peering, or you were not able to connect one Transit Gateway to the other Transit Gateway via peering. But of course, AWS has solved that problem now. It is possible to peer a Transit Gateway from one region to another region, and now sometime back they even started supporting peering within the same region. So which means, let's say you have a Transit Gateway in the Ohio region and you have another Transit Gateway in the Ohio region, you can peer these two Transit Gateways as well. So all of that is possible. Okay, now if you look at this comparison between Transit Gateway and VPC, Transit VPC, you will see the Transit Gateway surely has number of advantages, so you should look at using this. So Transit Gateway abstracts away the complexity of maintaining VPN connections, right? So that's what we were discussing. You don't have to get into creating VPN connections. Of course, with VPN connections, you always need to monitor them. You need to see if everything is okay there or not, right? Those type of things. You don't have to do that with Transit Gateway. Transit Gateway removes the need to manage and scale EC2 based software appliances. AWS is responsible for managing all resources needed to route the traffic. So in case of Transit VPC, right, we discussed that in case of Transit VPC, you have got EC2 instances on which some Cisco software is running. So of course, it becomes your responsibility to go ahead and monitor those EC2 instances and scale those instances as required. You don't have to do anything of that sort in case of Transit Gateway. Transit Gateway removes the need to manage high availability by providing a highly available and redundant multi-easy infrastructure. So Transit Gateway is, again, as I said, it's a managed service, so you don't have to really worry about its scalability, its high availability. All of those things are out from your plate. You don't have to do it. Transit Gateway improves bandwidth for inter-VPC communication to burst speeds of 50 GB per second per AZ. So it can support up to a good bandwidth, right? So of course, it also streamlines the cost. It is based on how much data do you transfer. Plus, in addition to that, there's a Transit Gateway charge as well, of course. Transit Gateway decreases latency by removing EC2 proxies and the need for VPN encapsulation. So in case of VPN based traffic flow, additional latency gets introduced. In case of Transit Gateway, that won't be the case. Now, though Transit Gateway is surely better in comparison to Transit VPC, but if you compare Transit Gateway with a normal peering, then there are certain points which you should keep in mind. There are a few things where it would look like that it would be better if you go ahead and use peering, right? So let's try and understand that. First of all, Transit Gateway has certain additional cost, right? So if you look at this cost which we are talking about here, in case of VPC pairing, if you just do the VPC pairing, there is no cost. But in case of Transit Gateway, there's an hourly cost. Once you set up the Transit Gateway, there will be a charge. even if you're not using it, even if there's no data transfer happening, even in that case you get charged, right? Now the actual data transfer charge is kind of same, 0.02 per GB, right? $0.02 per GB in case of peering and in case of Transit Gateway both, right? Though it gets divided in a different way, of course. In case of VPC pairing, 0.01 to the uh, 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 like to the one VPC and 0.01 to the other VPC owner, right? If they are there in the different account, then it goes to different accounts. In case of Transit Gateway, the charge will be there at the in that account where Transit Gateway is placed. That's where the cost will be incurred. So you have to understand that difference. So it's like in an organization where you have multiple business units, and if they are connected via Transit Gateway, then all the data transfer charges will be incurred in a central account, maybe your network account where Transit Gateway is actually created. Okay, so you need to figure out that how are you going to segregate that cost and charge it to every business unit, right? Overall monthly cost, so there is a comparison given here, of course, which you can look at. So if you do not have a very complex network where you have so many VPC connections and you are able to effectively manage with peering, then it's okay, you can just let it run with VPC pairing itself, right? When it is becoming mesh, that's where Transit Gateway helps you a lot. In case of VPC pairing, practically there is no bandwidth limit, right? In case of Transit Gateway, there is a maximum bandwidth limit of 50 Gbps per availability zone. VPC pairing really doesn't have any such limit. The bandwidth limit will be just dependent on the instances bandwidth limit, right? For example, you have instance 1 in VPC 1 and instance 2 in VPC 2. What is the bandwidth which is supported by those instances? Based on that, the upper limit would be. It doesn't VPC pairing as such, it doesn't have any upper bandwidth limit. Okay, so that's something to know. In case of Transit Gateway, there are limits, of course. In case of latency also, if you see, let's say there's a VPC A and VPC B, right? Two VPCs. So if they are directly paired, traffic just starts from VPC A, goes to VPC B. No additional hop in between. In case of Transit Gateway, first it will go from VPC A to Transit Gateway, then it goes to VPC B, right? In certain scenarios, if you have a very latency sensitive workload, right? And the traffic has to flow between two VPCs, there you might choose to go with direct VPC pairing and not use Transit Gateway, right? Because if your application is very, very latency sensitive, then this may be a problem. And the other one thing is the security groups compatibility. So what happens is, if you pair two VPCs, right? Let's say VPC A and VPC B, you can go ahead and refer the security groups of the other VPC in your rules. Okay, so what I'm trying to say here is that, let's say, it's like this. You have VPC A, right? And in VPC A, VPC and VPC B are paired, of course. So in VPC A, you have got an instance A. For this instance, the security group which is there, in that security group's ingress rule or inbound rule, you can put a rule, I'll write an example. You can put a rule like this. Let's say port is TCP, protocol is TCP, port is 22, and in the source, you can specify VPC B, whatever is its ID, / and you can put a security group ID from there, like something of this sort. So the good thing is that you can refer the security groups from the paired VPCs. But when you are connecting different VPCs using Transit Gateway, you cannot do that. So those are few advantages of peering over Transit Gateway. So there, in certain scenarios, you may still choose to go ahead and do peering and not go with Transit Gateway. Now the next model or the next pattern which you can implement is centralized egress to internet. What does that mean? It means that you can actually go ahead and just use a central VPC to to send out all the data out to internet. So consider that you have got, let's say, 4 or 5 VPCs, and some traffic needs to go out from all the VPCs to internet. Now one method is that you can go ahead and have a NAT gateway or 2 NAT gateways. Considering that it's production environment, you can have 1 or 2 NAT gateways per VPC, right? That can cost you more because a NAT gateway has a specific charge per hour in addition to the amount of data which it processes, right? So there are 2 components in NAT gateway pricing. So instead of creating like 5 or 10 NAT gateways, like basically NAT gateway in every VPC, what you could do is you can make use of Transit Gateway and send the internet bound traffic from all the VPCs to a central VPC, and from there you can send it out. Okay, so in order to do that, if you just see this diagram, in order to do that, you'll have to attach VPC 1 and VPC 2 to a Transit Gateway. So you know that what happens internally is that when you attach a Transit Gateway, or I should say when you attach a VPC to a Transit Gateway, an ENI gets created in that VPC, right? Of course, you get to choose the subnets, and we say that you should choose at least 1 subnet per availability zone. All of this we have talked in Transit Gateway video. So basically, in this case, what we are saying is that from these 2 VPCs on the left hand side, all the traffic which is bound to go to internet will first go to the Transit Gateway, and via Transit Gateway it will go to this one central VPC. We are calling it egress VPC, and here we'll have a NAT gateway via which traffic will go out, right? So if you just try to understand the routing, how are you going to do that? So let's say this is this is our VPC A and VPC B. These are 2 VPCs. So what we are essentially doing is anything which is internet bound, right? Internet bound traffic should be sent to Transit Gateway. That's what we are doing here, right? And in the Transit Gateway route table, you can see this is Transit Gateway route table. So here we are specifying that anything which is internet bound should go to egress VPC, right? And this is the egress VPC. If you see in the egress VPC, please see this carefully. This is one subnet and this is another subnet. And in these subnets, these are the ENIs which are created, right? These are the 2 ENIs which are created for the Transit Gateway. If you remember, we had discussed this, that whenever you are attaching a Transit Gateway to a VPC, if possible, go ahead and choose a completely separate subnet, right? You may go ahead and reuse the private subnets, it's possible, but the best thing would be if you keep a completely separate subnet only for the purpose of Transit Gateway. So if you see in this egress VPC, that's what has been done. So this is one subnet and this is another subnet, and in both the subnets you have ENIs created which are getting used by the Transit Gateway. And what happens, what is the routing for these 2 private subnets? You can see there is a route for NAT gateway. So which means when any traffic comes here, from this particular subnet, if the traffic has to go to internet, it will use NAT gateway and it will go out like this, right? So that's how it works. So just to say this again, from a particular VPC, which is like a spoke VPC, the traffic which is internet bound goes to Transit Gateway. In the Transit Gateway route table, you have this entry that if the traffic is destined to go to internet, it should go to egress VPC. And in the egress VPC, you have a route table which says that internet bound traffic should go to the NAT gateway. In this way, you can send all the traffic from multiple VPCs via this one egress VPC, or whatever central VPC, if you want, you can call it. But basically the purpose of this VPC is to send out all the traffic. Now the same pattern can be used to kind of bring all the traffic to a central VPC and then filter it as well, right? That also can be done, because all the traffic from your different VPCs are coming to one central VPC. So if you want to apply some filter here, that also you can do. We will try to show you that thing with a demo as well in one of the upcoming videos. So here is another example where instead of using NAT gateway, we are using a firewall or a network appliance hosted or installed on EC2 instances, so that any traffic which is destined to go to internet is able to go through this and it gets filtered, right? So like everything is same as you saw in the previous diagram. The only difference is that from these ENIs, when the traffic is destined to go out to internet, if you see the route table entry here, it says internet bound traffic should go to EC2-1, which is this one, right? So the traffic goes from this ENI to this machine. Whatever filtering you want to do here, that can be done. And after that, only the allowed traffic will be sent out via internet gateway. Same happens for the other availability zone as well. If you want to use a custom appliance or basically a filtering software on an EC2 instance, you can use this mechanism. But in this case, managing these EC2 instances is your responsibility as a customer. You will have to take care of it. AWS has introduced a managed solution for this as well. We'll surely cover that in one of the upcoming videos.